Okay, our last topic from the Monday, March 16th lesson that we did in class is one of my favorite mathematical names, and that is a gentleman by the name of L'Hopital. So that's his last name. And what we're going to study is something called L'Hospital's Rule. And if we get some time at the end of the video, I'll do some fun facts about L'Hopital, but right now let's get you what you actually need with it. So L'Hopital, it's evaluating limits. So it's a limit evaluation rule. So limit evaluation. And it specifically has to do with limits that are called indeterminate form. So indeterminate form. So those multi-syllable ones are hard with this format, but we'll do them. So as a for instance, indeterminate form is something like this. So if I have a limit as x approaches infinity, and I'm doing the ln of x over the square root of x. With any limit, and we'll call this problem 1, if you plug in infinity on this, because that's ultimately what you're doing, is you're saying I'm getting really close to a big number, you're going to have ln of infinity over the square root of infinity. And that's infinity over infinity, or it's really big over really big. So I'll just write that. It's big over big. And I know that's a really technical term, but that's, as good as any to think about it. So big over big, and we don't really know what that is. If these two bigs are like the same relative bigness, then that would be 1. If the top big is double the bottom big, then it would be 2. If the top big is astronomically larger, infinitely larger than the bottom one, it would be infinity. And if the bottom big was really, really, really big by comparison to the top, we'd have a 0. And we don't know. We can't tell. It is not determined. It is indeterminate. So when you have something like infinity over infinity that you can't numerically evaluate, you have a case where you could use L'Hopital's rule. The way L'Hopital's rule works is it says we're not able to compare the y values at infinity. So instead, let's compare the rates of change at infinity. What I mean by that is the actual method that L'Hopital's rule uses, and I'll write that in there because this has got to be your takeaway, is you are going to take the derivative of the numerator and denominator separately. And the reason you're going to do it separately is to look at the rates of change separately. So for this one, I'll keep going in my red to distinguish what we're doing. We're using L'Hopital's rule, so that part still is the same, but now I'm going to take the derivative of the top. Derivative of the numerator is 1 over x. Derivative of the denominator, derivative of the square root of x. So that's x to the 1/2. If we take that thing's derivative, it looks like half x to the negative half, or another way to write that is 1 over 2 square root x. Notice this is not the quotient rule. And it's why I wait till much later in the year to talk about this. This is not the quotient rule. We have a quotient. We have something that's being divided, and that's what creates the recipe for L'Hopital's rule. But we are not taking the derivative of the whole thing. We are doing the derivative of the top and the bottom separately. And that's the takeaway we have to have here. I still can't evaluate this thing the way it is, but we can do some algebraic adjusting. So I'm going to take, and I'll make sure I keep writing this limit expression out there. I'm going to take and multiply by the reciprocal of what's on bottom. So I'm just going to flip the bottom and multiply, and let's see, I'll move up. So I'll knock that out with an eraser. That little guy, I was going to put an equal sign there, but better to just keep rolling with this. And I'm going to do some canceling. So let's see. I've got an x to the 1/2 up top, and I've got an x to the 1 on the bottom, which means I'm going to have a x to the 1/2, or a square root of x on the bottom, and I've got a 2 up top. So it's just multiplying across the top, across the bottom, and canceling the x powers. Now infinity goes in, and I've got 2 over infinity, or 2 over big. So that's actually using the limit or applying the limit, and 2 over big is 0. So 2 divided by something really, really big is 0. So what this means about this problem is this original big over big we were looking at, it means that the bottom big was very, very, very large with respect to the top big. And we can't see that here. So we can't see it in this first form. So then what we do is look at the rates of change. The idea being that if we can't evaluate the actual number, but we could look at how is it changing, that's saying that the top and the bottom are changing at very different rates. The bottom is changing very, very quickly or rapidly in comparison to the top. So it means even if both numbers are big, the bottom number is getting big at a much, much faster rate. And that's what L'Hopital's method is doing. It's comparing the rates, or it's looking at the derivative of the numerator and denominator separately. And it only gets used with indeterminate forms. So this is specific to indeterminate forms. And we need to look at further examples and do more practice with this, but this was just the introduction that we gave to the topic on Monday in class. So another example, let's see, we could do something like the limit as x goes to infinity of e to the x over x squared. So again here, you put an infinity and you're going to get big over big, and I'm not going to go through that whole big over big deal again. So instead, we'll use L'Hopital's rule, or we'll apply the idea of taking the derivative of the top, which e to the x is nice, its derivative is e to the x, and the derivative of the bottom, which is 2x. So 2 goes out front, x is there, you get it. The infinity is going to go in, and it's still big over big. So it didn't work, at least not on the first application, and that means we need to do a second application, and that's the method with L'Hopital. You just keep doing it until you get to something that can be evaluated. The derivative of e to the x is still e to the x, so I've taken another derivative, but I've still gotten the same thing. But the derivative of 2x is 2. And in this case, now I can apply the limit. E to the infinity over 2. E to the infinity is infinity. Infinity divided by 2, and it's not always 2. I realize I've just chosen two examples where I get a 2 here and a 2 here. It's not like 2 is always going to show up. That just happens with these derivatives. So I get something really big over 2, which is infinity. That one means this top infinity, e to the x, far outweighs the bottom infinity. And this one's probably actually a little easier to think about because we're used to the idea of an exponential jumping up really quickly. And a parabola goes up, just not at the same rate. But when you get really big, you get two really big numbers. So instead, what we're going to do is compare the rates of change and say, well, that top big number is changing much, much more rapidly. So even though we can't tell, it's indeterminate, we can look at the rates of change and say that the top is much, much bigger than the other. And it doesn't just have to be to infinity. We could go to other values as well. And so I'll do a third problem here. I'll scroll down and I'll do a third problem that we did in class where instead of going to infinity, we went to a number. So we'll go to a number like 1. And when you see that, when it's a non-infinity number, think vertical asymptote. Think I'm probably approaching some kind of vertical asymptote, or it could be a hole, but I can't algebraically do any adjusting. So again, with any limit, you plug in a 1. So in this case, 1 goes in. Well, ln of 1 is 0. 1 minus 1 is also 0. 0 over 0, but again, in limit land, that's not really 0. That's just representational of small. So that actually means small over small. But I don't know which small is smaller than the other, if I can kind of play off the big over big deal. So it works the same way, where we have to wait how quickly those smalls are changing. And so this is another indeterminate form. So one indeterminate form is infinity over infinity. And maybe I'll just write that off to the side. So indeterminate forms, indeterminate forms would be 0 over 0 or infinity over infinity. There are others, but these are the heavy hitters. These are the two big ones that come up over and over and over again. And we'll take a look at the others when we drill in a little more in lessons. But in this first introduction of it, these two are good to look at. So we've got 0 over 0. And then what we'll do is we'll apply L'Hopital's rule to this because it fits our indeterminate form. And I'll do derivative of the top, which is 1 over x, and the derivative of the bottom, which is just 1. And now I'm going to plug that 1 in, and I get 1 over 1 over 1, which is 1. And what that means is these two little numbers, these two smalls, are changing at roughly the same, or not roughly, they're changing at the same rate when you get close enough to 1. And so the value that this thing takes on is 1. And it's not infinity, it's not 0. This one actually has a numeric value. So you get 3 potential outcomes when you do indeterminate form. So there are 3 potential L'Hopital outcomes when you apply his rule. You're either going to get infinity as your result, you'll get 0 as your result, or you'll get some number where the top and the bottom actually have a relationship locked in with each other. And that number doesn't always have to be 1. It could be another numeric value, and it could be a plus or minus infinity. So I shouldn't just say infinity. It could be a positive or a negative infinity. And we need to look at more examples, and we will, but this is just kind of a primer or an idea as to what L'Hopital's rule is all about.